All right, here we go. So, on this one, again, to recall, just in case y'all were not here, was this on the whole time? Ooh. Um, to basically use this link from Google Classroom, you're prompted with this. If you hit the play button, it'll allow you, it won't be grayed out no more and allow you to fix things. And then you can just drag these options. So if I just redid it one more time, so I'm going to drag it to 2, and I believe it was 0, 0, 0, 2, 0, 0, 0, 2. So we end up with this green box here, and we basically on step 1 we graphed it, done. Step 2, we asked ourselves what is the volume. So we started off with, hey, this is a cube. What's the how do you find the volume of a cube? Good. Length times width times height. What is the length, width, and height of this green cube? 2. So then 2 times 2 times 2 is 8. We also can see then all we have to really do is multiply by the diagonal as long as the other numbers are 0, because then we just get 2 times 2 times 2, which again is 8. So this basically will turn, so again, we would have, so for our second thing, for the volume, would just be 2 times 2 times 2, which is 8. But this is not just for cubes. This works for any type of prism that we have. So if we have a rectangular prism, we could still multiply that diagonal, which is what we see in part B, which we'll do here in a second. But the third thing it asks to do is find the inverse. Now, to find the inverse, that is when you multiply by something to bring it back to 1. So currently, it is a 2 by 2 by 2 matrix. What would I have to multiply by 2 to make it back to a 1 by 1 matrix? 1/2. So what do you think the matrix will look like in order to multiply a matrix of 2 0 0 0 2 0 0 0 2 to bring it back to? So basically the question is, we have this, which is what this is right here. What do I have to multiply by to get it to back to where it was? Perfect. I can multiply by 0.5 or 1/2, however you want to write that. Let's just do that first row to verify that's what we get. How would I multiply this out? How do you multiply matrices? Row by column. So 2 times 1/2 is what? 1. And then I would want to multiply by 0 pretty much by anything, because what's 0 times whatever? 0. So let's just say 0, but it could technically be whatever. And all that would add up to 1. But the issue comes is, oh man, and so I come up to the second one. I want to keep this a 0 times that 1/2 in order to multiply the rest of them by 0 so that I get the 0. And then same concept here. I want to keep these all 0 so that I still get the 0 there. Let's look at the next one. We could do 0, 1/2, 0, row by column again. Let's take the middle row times the middle column. That would give us that middle number if it does give us a 1. 0 times 0 is 0. 2 times 1/2 is, and then 0 times what would give me 0? Anything, right? But we'll say 0 for now, and that does give me the 1 there. So with that pattern going, I can see what's this last number going to be? A 1/2. So it sounds like you're doing a lot to find the inverse of something, but really you're just trying to figure out, what do I have to multiply this to make it a 1? And for now, while it's a pure dilation, because that's what this order would be, I can just figure out the inverse, which means just flip the fraction. Any questions there? All right, so let's look at part B now. Go ahead and take this time and adjust your matrix on your computer to make it the 4 0 0 0 1 0 0 -2. While you're doing it, I'm going to try to do it myself as well. You're just graphing it. So you're going to take the 4, 0, 0, 0, 1, 0, 0, 0, negative 2, and just see what your prism does. You should only have to change these middle three numbers. The rest of it stayed 0. Does everyone's shape look like this? All right, so the second part of the question again asks for the volume. Now let's pretend we didn't catch that pattern of the diagonals there. How do I find the volume of a prism? Length times width times height. The only difference with a cube is length times width times height ends up equaling the same thing. So we could actually have said S cubed, but it's pretty much the same thing as if you were looking for a cube. Now I can kind of look at this right here. If you didn't know, this is the y-axis, this is the z-axis, and this is the x-axis. It labels it right here for you. I got lost when I was studying it first. I was like, how do I know which one's the x? Because the only thing I saw was y. Then I went back and I was like, oh, I see it now. So this is, so what it is this is the XY plane and the Z is going through it. So that's what makes it three-dimensional. So technically beforehand, we were just graphing this square. Now I made it three-dimensional by making it come up. That's why it's on the Z axis here. Yeah. So that's what you would look at. You go here and you go 1, 2, 3, 4. The length would be 4. What would be the width? Looks like just 1. And then the height would be, well, we don't count distance with negative numbers. So instead of a negative 2 would be what? Positive 2. So if we were just ignoring this matrix altogether, we would say, well, this is a 4 by 1 by 2, and we would multiply those out. So what it comes down to, if you're trying to identify this pattern, you have to use the absolute values of these since we don't have negative distance. So this would be 4 times 1 times the absolute value of negative 2, which gives you that depth of 2. All right, so we're looking for the volume. Again, this is going to be 4 times 1 times the absolute value of any negatives. And what does that give us? 8. Right. Questions on why that negative has to be treated as a positive. We don't have negative distance, right? So even though we're going below our, like as if we were digging a hole, we don't go, we're negative 6 feet underground. We go, we dug 6 feet underground. It's a positive notation in a direction of what we say. So either up or down, but it's still positive direction. All right. So with that said, the third thing is trying to make that matrix have an inverse. So again, this is what we have. What do I have to multiply by in order to get back to my unit cube? With that same concept that we saw with the 2. So let's start with this, the 4. What would you have to multiply by 4 to make it 1 again? 1/4, all right? And we saw, just like with the 2, that entire row became zeros again. What do I have to multiply 1 to go back to 1? 1. Don't say nothing, because 1, you would still have to multiply by 1 itself. So this now becomes 0, 1, 0. That's usually the biggest mistake, is students will just say 0 right there because they're like, oh, you don't do anything with 1. It's already 1. But you still got to multiply by 1. And what do you think you have to multiply by? -2 to get back to 1. Good. -1/2. A lot of students will also just forget the negative as well. So make sure you have the -1/2, because what is -1/2 times -2? +1. Those two negatives make that positive. Any questions on how to find the inverse? With pure dilations, it's pretty straightforward. It's different when we bring in rotations. All right, I want you to try C on your own. Graph it, find the volume, and then see if you can find the inverse. And then we'll come back together to check it, and then talk about what happens if it's not a pure dilation. And then remember that part 2 is asking for the volume. Area or volume? Yeah. Because now you have a three-dimensional shape that has turned into a two-dimensional shape. So it has area, but no volume. Take this piece of paper right here. Oh, do this. Take this stack of papers I got. This has volume, right? Has length, width, height. Now we just take it down to just this piece of paper, and let's pretend there's no depth there. Does this have volume? Just an area. Yeah. Now technically that piece of paper has volume because it has a, I don't know, is it like 0.002 centimeters or something like that? Oh, yes. Sorry, I thought you had a question. Ready? We all think we have an answer? No, but we're ready to go over it. All right. So let's graph it real quick. You should have gotten, let's see, 4 should stay there. This, I think, became a 0 and the -2. So basically, that was the only thing you had to do. So what happened to our three-dimensional shape? It went flat. So before we do any math, realistically speaking, does this have volume now? No. And if we do our math and we multiply this by the diagonal, what is 4 times 0 times the absolute value of -2? 0. So that logically also makes sense. So it's more of a visual and algebraically. So the volume again would just be 4 times 0 times the absolute value of -2, which would just give me 0. And it makes sense. Did y'all find out what the inverse of this is? Why? There it is right there. When I look at this matrix right here, 4, 0, 0, 0, 0, 0, 0, 0, -2, I can see, well, I can multiply that by 1/4, 0, 0, and I can multiply this -2 by 0, -1/2. But how do you turn what do you have to multiply 0 to turn it into a 1? You can't, because no matter what number you come up with, it's still going to come out to 0. So this has no inverse. There's no way to take a two-dimensional shape back to a three-dimensional. Questions? All right. So let's find out what happens to matrices when it is not a pure dilation. So if we kind of, let's see, clear this. Let me go back to that page. So part D says, again, altogether now, describe the geometric effect of a transformation of A000B000C. Board numbers A, B, and C describe when such a transformation is invertible. Basically, what it's stating is if you need a invertible situation, this would be 1 over A, 0, 0, 0, 1 over B, 0, 0, 0, 1 over C, as long as A, B, and C does not equal 0. If either one of them was to equal 0, then it's not invertible. Inverse, like it's, you can find an inverse to bring it back to 1. That's 1 over A, 1 over B, 1 over C, as long as that's a comma. That's an arrow showing that this is the, it's invertible if this happens. So you can write it like this as long as A, B, and C does not equal 0. Because if it does, we just saw that it was false. All right. Something else that you can add into this as well is the A actually dilates the x-axis. The B dilates the y-axis. And the C dilates the z-axis. And if we were to multiply this out, this would kind of make sense because this is a times x, and then these zeros would cancel out y and z, and you would only be left with ax. Same concept if this row to this column, the 0 and z would cancel out, and I only have b times y. And then this row times this column, the zeros would cancel out x and y, and I would literally only be left with cz. So when it's written like that, that's why it only affects these corresponding axes, which is what we saw when we expanded it. We saw the x, y, and z axes change depending on what values those were. Any questions on that? So that's bringing all your pure dilations. So let's move on to the exploratory challenge part 2, looking at non-pure dilated functions. Now, a lot of these things, they want you to do it and then see if you can come up with a conjecture, meaning can you come up with your own opinion? I'll kind of geared you towards where you need to head, but go ahead and try to plug these things in. One thing you're going to struggle with is when you come over here, obviously I can plug in a 1, right? Because that first one's a 1. Can you change 0 to cosine of 45 degrees? No, we need an actual number. So use your calculator and go ahead and figure out what is cosine of 45 degrees. What mode should my calculator be in? Degrees, right? Now, obviously, we could look over here, but this gives us the square root of 2 over 2. You still don't have that as a decimal. And with this function, we need decimals, at least the tenths place. How do we do it? I got you. Let me just bring up my handy dandy calculator over here. One half would be closer to 0.5. Square root of 2 over 2 is going to be closer to the 1. So maybe like 0.75, 77, something like that, maybe. Oops. Oh, is it 0.70? So yeah, so there, yeah, I was like, I was thinking almost a quarter. Yes, I'm working on it, but something just went wrong. Hopefully that was just an error. That's not going to be something that's continue to do that. Hold on. I did. Oh, cool. I'm glad that worked. Sign in successful. I was like, if it wasn't for Google, I don't know if I can remember any of my username and passwords. All right, so I'm just going to go to regular calculator, and the trig buttons are right here next to the 7. And for us, it said cosine. I'm gonna hit cosine. Pay attention to the top right of your screen. Make sure it says DEG. If it says RAD, all you simply have to do is literally just click on it, and it changes like that. All right. You used to have to go back into settings, change settings, come back, reopen a page, but now you can just change it there. Just make sure it says DEG on the top. And then you just type in whatever the degree is. You do not have to worry about putting the degree sign. You just type the number and then hit enter. And now for this program, you only need to round up to the tenths place. So what value would this be? 0.7. Any other questions on that? And if I wanted to do sine, I would just do trig. Now I choose sine, type in my number, and what is that value? 0.7, which again makes sense because at 45 degrees, square root of 2 over 2 and square root of 2 over 2 are the exact same numbers. All right, let's bounce back over here. I'm coming back over here to graph it. So now I'm going to go back. I'm going to graph 0.7. There we go. And then it's the next one says negative sine of 45. So that means that's going to be a negative 0.7. And then this is a positive sine over 45. So that's going to be a 0.7. And then this one looks to be like a positive cosine. So that's going to be a positive 0.7. Yeah, there we go. So everyone's shape. I was like, that looks lopsided. What happened? All right, go back to 1. Still looks lopsided. Maybe it's not. Maybe it's just y'all look lopsided. It is. So it's not supposed to be lopsided. It's supposed to look like it does. It's supposed to look like it actually just rotated. So it's actually saying, go ahead. Maybe because we had a round to 0.7 versus 0.0. You're probably right. So it's probably a little off due to this rounding here. But this is actually a rotation. So we no longer see a dilation, but now we see a rotation. And what do you think the rotation is? 45 degrees. Those two things, really easy to point out. The hard part is rotated around which axis now? Jacob, why do you think the X? Exactly. That's a visual way. What else could we look at if we're just looking at the matrix? What doesn't get affected? The x-axis. That first row there, that first row of 1, 0, 0 is doing nothing to the x, because typically you would multiply to some random coordinates. That's what this is represented, some random coordinates on the blue one. I would multiply it and it would still just be an x with no y and z, versus the other ones being affected by the y and the z, and the 0 had gone away. So this is a, see what it wanted us to do a few things. To come up with a conjecture. So we can say this rotates around the x-axis 45 degrees. Which direction? It would be counterclockwise. Remember, for our unit circle, a counterclockwise motion is positive direction. Clockwise is actually a negative direction. See the rotation? Oh, I agree. So when I was doing this at home, I was like, you're going to have a hard time really determining that this is rotation. So I was trying to identify what you can look at on the matrix. So just in case our graph is a little off or you're having a hard time looking at it, when it's written in this form, we can say it's going to rotate. And because the x-axis doesn't get messed with, we can say it rotates around the x-axis. Because what you're going to see here in a second is I'm going to move this. I'm going to shift it in different spots, but there's still going to be one row of just a 1 where that axis is not being affected.
So the one with the whole like it's a row with like the 1 is the one that
is being rotating around. Yes, sir. So again, this rotates around the x-axis 45 degrees counterclockwise. And just like in module 1, this is a very specific word that you need to make sure you write in your test. Clockwise would be incorrect. Yes. So if I was to have sine and cosine of negative 45, now I can say the same thing, but now clockwise. Right? Yeah, go ahead. That's fine. Oh, what were you thinking? Could say that way as well. Yeah, you could say because that would be its counter argument. Clockwise is 315 would be the same thing as counterclockwise 345 or 45 degrees. You're right by saying that. True. Well, technically, since circles are infinite and they just kind of go round and round, you could actually probably come up with an infinite amount of answers. I could have technically said, let's rotate was at 405 degrees counterclockwise, and I would still land in the same spot. So even though I'm only going 45 degrees, I could technically go with 405 degrees and I'd be landing in the same spot, even though I didn't really rotate a full circle. It just lands in the same spot. Off the degree in the matrix, yes. So specifically, yes, if it's positive, counterclockwise. Even though where you land in those statements is true, what they're going to specifically look for is given 45 degrees, it's counterclockwise. Had it been negative, now we can say clockwise. All right, so now when we move to part B, again, it's just asking you for the geometric transformation of these guys. So let's, I'll do one more with you, and then I'll kind of let you kind of play with it. Well, actually, I'll do two more because technically that second one's the same thing. Oh, actually, no, it's not because it's a negative 45. So in y'all's calculators, again, this is looking at part B, I. What is cosine and sine of negative 45 degrees? Is it? Not both of them. Good. For cosine, you should still get 0.7 because again, negative means clockwise. 45 degrees would land me here. So cosine's still positive, but sine will turn into negative. Perfect. When we write the numbers, yes, but watch out because it's the equation is on one of them it's like negative sine. So we're on part B, I, and it said rotation by negative 45 degrees about the x-axis. So yeah, so that's what I was about to work on. So my little matrix here. Again, it's about the x-axis, so therefore I know that this first row is just 1, 0, 0 because what's not being affected because it's being rotated around that. And then it would be 0, and then the formula is always cos. Well, it's basically it takes this two-dimensional geometric effect that we had when we dealt with a square, and that's what goes there. So it's always going to be a positive co, a negative sine, positive co, depending on where you're locating it on, depending on what axis you're going on. So that part will kind of move within our three-dimensional matrix. So again, x-axis not being touched. So therefore, you can almost fill this part out. That part's already done. Once you know you're rotating around whatever axis. Y'all good, gentlemen? Okay. I don't know if you had an argument or a question or something. Oh, yeah. All right. So this would then be cosine of 45. Negative sine 45. Well, I guess negative, sorry. This is going to be a lot harder to write. So cosine negative 45, negative sine negative 45, sine negative 45, cosine negative 45. Right. And again, I know where those trig functions are going because again, it's rotated around the x-axis. So then you take that, and I guess really and truly, we don't have to graph it here. So let me do this to kind of help you. That's where you are at right now. So then I can just turn this into 1, 0, 0, 0.7, right? I say that. So when we use that program to graph it, you need to convert it into a decimal to make it 0.7 so that you can actually see what it is. When you have to do this work on the test and it just wants the matrix, you have to keep them in the fractions that are on the unit circle. So in this case, since I'm looking at negative 45, I'm really looking at 315 degrees. So what this is going to look like is the square root of 2 over 2. And then this would be a negative square root of 2, which will make a normal square root 2 over 2. And then this one would just be negative square root 2 over 2. And this one is the square root 2 over 2. So this is the answer that it would be looking for on the test. If you have to graph it using that program, you would have to turn it into a decimal so that you can actually type it in. Does that make sense? So if I just strictly say, hey, come up with a matrix that has this geometric effect, this is what the answer needs to look like. Go ahead, ask the question, David. Trying to find out the signs. Okay, so negative 45, but it's at 315. You agree with that? So that means that cosine's still positive. So that's why these two stayed at positive square root 2 over 2. Well, we're at negative 45, so that's why we're at 315. And then sine would be negative square root of 2 over 2, right? So it's become a negative, negative, which turn it into a positive, and then this is positive, so it stays negative. So we're good with that? Do you think you can try one on your own, or you want to do one more together? With your faces, let's do one more together. All right, so this one's a rotation of 45 degrees about the y-axis. So let's start with the y-axis. I don't want the y-axis to move. So which row deals with the y-axis? The middle. Okay, so that's going to be 0, 1, 0 in the middle. But just like the middle row deals with the y-axis, the middle column deals with the y-axis. So I'm also going to have a 0, 1, 0 there as well. Just like here, row 1 of the x-axis and column 1 was the x-axis. So in this one, the second row or middle row, however you want to look at it, will deal with the y, and so will the column. Does this look good? Does everyone understand why I have a T of zeros? Okay. So then these spots will play out like that over there. So this would be cosine of the degree. This would be negative sine of the degree. This would be sine of the degree. And this would be cosine of the degree. In this case, the degree was 45 degrees. All right. So questions on how to get to this point. After that, you're just using the unit circle and plugging in the fractions. So what would this look like? There you go. Makes sense? I like your dance movement. It's good. All right, go ahead and try 3. I don't want you to go too far. I want you to just try 3, see if you can get the right answer. And then when you build your confidence, we'll keep going with it. If you think you got it, you're more welcome to keep going on. Good, Jacob? So on this one here, z-axis. Which row deals with the z-axis? The bottom one. So the bottom row, I can already go ahead and write it out. That's it. You would put them because if the last row deals with a z, that means the last column will deal with z. So that's where the random zeros would go. And then your 4 other spots there, you would use the cosine, negative sine, sine, cosine pattern. So you move from left to right. So the first row that's available from left to right in their corresponding elements, we get cosine, negative sine. The second row that's available in their corresponding elements will get sine, then cosine. And that's the pattern it follows. Hannah, you already got the answer? Hannah? Totally? Are you totally lost? I feel that's a Monday. All right. Does everyone got the third one done? All right. So once you know it's a rotation around a specific axis, I like to start with that one first. So again, z-axis deals with my last row. So that would be 0, 0, 1. And then if it deals with my last row, it also deals with my last column. So it's going to be 0, 0, 1. And then going in the rotation, this is going to be cosine of 45 degrees, negative sine of 45 degrees, sine of 45, and cosine of 45. Now, one thing you'll start learning is when you start kind of identifying the patterns, you might be able to go straight to the answer. I'm good with that. Once you kind of figure out, all right, this is how 45 is going to be these fractions, I'm good with you going straight to the answer. So this is what we should have gotten. We all good with that? Do you want to try 4 on your own now? Then with 90 degrees this time, so now your coordinate's going to change. If you think you got it, go ahead and you can identify an equation for both all rotations around the X, Y, and Z axis. Are we done with 4, I assume? Okay, I'll give you some time. We good? All right, so x-axis, again, that tells me that this is going to be 1, 0, 0, 0, 0. Get that part down. All right, 90 degrees. I'm going to go to 90 degrees. What's my coordinate at 90 degrees? So everywhere there's a cosine written, that would be a 0. So this is cosine of 90. This is cosine of 90. This would be negative sine of 90. And this is sine of 90. So again, where there's a cosine 90, it gets a 0. And then what's sine of 90? 1. So this becomes a negative 1 and a 1. So this is what a rotation 9 degrees around the x-axis looks like. We good with that? Have you already done the 5th one? Yes. Am I about to run out of time? Oh, I think it's 40. Okay, so I got some more time, but I want to wrap this up. So 5 here, let's make sure we got it right. Y-axis, this is 0, 1, 0, 0, 0. We're good with that first start. All right, then cosine of 90 would mean that this is 0 and this is 0. And then sine of 90 means that this is negative 1 and this would be 1. Is that what we all got? Heck yeah. Rotation's way harder than dilations. So if you're getting this, Ain't getting much harder than this. These are rotations. The first one that we had were dilations. Now we're rotating around the axis. Oh, what was the last one, guys? Hold on. There we go. Okay. All right. Z axis. So this would be Z, whatever the fifth one was. Okay. Okay. I can hit the back button. Hold on. We'll just hit the back button. It was 0, 0, -1, 0, 1, 0, 1, 0, 0. Okay. All right. So again, this would be Z axis. So that'd be 0, 0, 1, 0, 0. Cosine of 90 would be 0, 0, and then -1 and a 1. Well, I'll go with that. All right, so these are going to be what you're probably going to use when you take the test, because you're just going to take these equations and just plug it in and get your information. So anytime I'm rotating purely around the x-axis, because obviously you'll find out that we can rotate around many axes, but a pure x-axis rotation will be a 1, 0, 0, 0 cosine theta, negative sine theta, 0 sine theta. Oh, that looks like a theta. Oh, it's just a 0. Sine theta, cosine theta. All right, so this is your equation every time, and then we can make the next two as well. So this would be cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And then our last one, cosine theta, negative sine theta, 0, sine theta, cosine theta, 0, 0, 0, 1. All right, so now when you have these pure dilations, you can literally just go plug them in, get your equation or your fractions or your whole numbers. Well, not an identity matrix, but like a matrix equation type thing where like when you get like a formula and you can just plug in the numbers like volume or something like that, and it'll pop out the answer. It's kind of what this produces for you. All right, so the last part, if you flip to the very end there, it says describe the geometric effect of all these. So how do you know that? I thought you said we got it at 45. That's 2 minutes. Yeah, I like to round up though. Optional. My fear of not doing the option is what if it optionally shows up on your test? For today, we'll optionally not do it. But I'll look at the test and see, is this going to show up?